Volcanic eruptions exhibit a range of behavior from a little bit more quiescent eruptions to other eruptions that are more violent. The quiescent eruptions produce these like outpourings of fluid lava, and we call them effusive. The more violent ones are like the one that you see in the bottom right picture, and we call them explosive. There are two primary factors that determine how magma erupts, and those are viscosity and gas content. The viscosity is a function of the silica content, which in turn is a function of the composition and the temperature of crystallization. So depending on what types of minerals that melt has, and depending on the temperature at which they crystallize. The more felsic magmas contain a lot of silica, so they are high in silica, which makes them flow incredibly slow at almost imperceptible speeds. They form these short and thick flows that again are very, very slow. More mafic magmas have low silica content in contrast, so they are relatively fluid and have been known to travel over 150 kilometers before solidifying, so a long, long way before they crystallize. They travel quite fast. Temperature has a huge role here as well. The hotter the magma, the more fluid it is, just like caramel syrup, for example, as you're seeing in the image on the bottom left. When caramel syrup is hotter, the more fluid it will be. So it works the same way. The hotter it is, the fluid it is. The lavas, when they begin to cool, they begin to slow down, and the viscosity within the flow increases. The gas content, or otherwise named the amount of volatiles within the melt, is the second factor that determines whether an eruption will be effusive or explosive. It is influenced by the confining pressure and the viscosity as well, but mostly by the confining pressure. The common gases in volcanic magmas, as I have said before, are water vapor, CO2, and SO2. These gases tend to come out of the solution that they're in once the confining pressure is reduced. This is analogous to how CO2 escapes from bottles of soda, for example, as a Pepsi or Coke. So when the cap is on, I should say, the pressure stays within the bottle, but once the cap is released, then the pressure is also released and the gases rise and escape. So you see most of the bubbles rising towards the top of the can, and hence creating that sort of explosive behavior that it has. So if there is too much pressure above and little flow, there will be a high amount of gases that are building up. The more felsic magmas typically contain large amounts of gases. This is due to their composition, which causes the melt to be more viscous and hence have less flow for the gases to escape. And this is also because of the environments under which they form, which are typically under a lot of pressure. The more mafic magmas, by contrast, typically contain small amounts of gases, and this is also due to their composition, which causes the melt to be less viscous and have more flow, and also because of the environments that they form in, which are typically areas of low pressure. So now here we will look at effusive eruptions first, and then we will look at explosive in the next few slides. So effusive ones, these are the more characteristic eruptions in mafic magmas, or of mafic magmas, I should say. All magmas contain some water vapor and other gases that are kept in solution by the immense pressure of the overlying rock, as we said in the last slide. As the magma rises, or the rocks confining the magma fail, the confining pressure above drops, causing those dissolved gases to separate from the melt and form numerous tiny bubbles, as we had said before. When fluid basaltic, or I should say more mafic types of magma erupt, these pressurized gases escape fast. At temperatures as high as 1100 degrees Celsius, these gases can expand to occupy hundreds of times their original volume inside of those bubbles. So sometimes these expansion causes the need to escape, and that is what propels the lava fountains dozens or even hundreds of meters into the air at times, like the one that you're seeing in the bottom left. Eruptions that involve the fluid basaltic lava flows characteristic of Kilauea typically occur due to a new batch of molten rock that accumulate in the magma chamber near the surface. These events can usually be tracked by geologists, since the summit of the volcano usually swells a few months or even years prior to the eruption. So they're pretty well monitored. All right, now we will be looking at the explosive type of eruptions. These are more characteristic of intermediate or felsic magmas. Remember that felsic magmas have a relatively high gas content and also that they are quite viscous. As the magma body rises, the gases stay in solution until the confining pressure lowers enough so that they may separate and form those tiny bubbles that increase in size. Because of the viscous nature of those felsic magmas, the bubbles are usually trapped inside of the melt. When the pressure exerted by the increasing magma body size overcomes the pressure from the confining rock that is surrounding it, and usually above it, then there's fracturing that occurs. As the viscous magma begins to move up through those fractures, a further drop in pressure occurs, hence enhancing more bubble creation. So this chain reaction often generates what is an explosive event, where magma is literally blown into fragments of ash or slightly larger particles that are usually carried very high up in the sky by the escaping hot gases as well. So it is common that explosive eruptions occur in many different episodes as the gases are released. So the pressure in the remaining magma body drops when these are released, and then it starts to build up again, to then erupt again. So it's a continuous chain reaction that is occurring. All right. So again, I'm gonna say all those things again because they were a little bit complex. So in those felsic magmas, high in gas and viscous, when the body of magma rises, and it is under a lot of pressure, what will occur is that the overall body of magma has to overcome the pressure from the overlying rocks in order for the gases to increase in size and push up everything, making a violent explosive eruption. Okay? If you need to go back in the video and hear me say the whole spiel, definitely go ahead and do that. Okay, the explosive nature of this type of eruptions is why they often form the eruption columns of ash and gas that you're seeing, for example, on the left bottom picture. And these can rise up to 40 kilometers into the atmosphere, so way, way high up. These type of eruptions are usually the most harmful to living organisms, and this is due to the different deposits that come along with them, or the different gases that are also ejected from them. The picture to the right is one of the common phenomena that occurs with volcanic eruptions that have eruption columns, eruption columns like the one that you sort of see. It's kind of hard to see it since it's nighttime and it is raining. But lightning flashes have been observed over large volcanic eruptions many, many times now. Scientists think that the charged particles responsible for the volcanic lightnings may originate from both the material that is ejected from the volcano and also through the charge formation process within the ash cloud that moves through the atmosphere. So it's kind of a complicated hypothesis that is, being developed, and only few scientific studies have been conducted on this volcanic lightning, at least up to now. So it is still a little bit of a mystery overall, but it's definitely beautiful and it has been documented many times already. Okay, so now we'll be going to through the different materials that are typically extruded during a volcanic eruption, whether that volcanic eruption is effusive or explosive, and I'll clarify that when I'm explaining the different features or materials, I should say. The first material or feature that we'll look at are lava flows. About 90% of Earth's lava is estimated to be mafic or basaltic in composition. Remember, basalt is a mafic rock, and most of the times or not most of the times, it's always an extrusive mafic rock. So when I refer to mafic lavas, it's almost always going to be basaltic composition. So I'm going to say that interchangeably during the lecture. Mafic and basaltic in composition for volcanic eruptions. So about 90% of them are of basaltic composition. Most of those lavas erupt on the seafloor through submarine volcanism. Lavas that have an intermediate composition account for most of the rest of that 10% that remains, which leaves rhyolitic lavas to account only for about 1% of the volume of lava on Earth. Most rhyolitic eruptions tend to erupt pyroclastic material rather than lava flows. And when they do erupt lava flows, they're incredibly slow and barely perceptible. So here we're still talking about basaltic lava flows. On land, hot basaltic lavas, which are usually, again, very fluid, generally flow in thin and broad sheets or stream-like ribbons. Fluid basaltic lavas have been clocked to travel as fast as 30 kilometers down steep slopes, but more typically they flow about 10 to 300 meters per hour. In historic past, very large basaltic flows have occurred, some of them close to home, making the Columbia River basalt igneous province. As you can see from the picture on the top left, each subsection of that cliff is a different flow. So there were many in different episodes that occurred of these massive lava flows. They were all associated with a mantle plume underneath from where they happened, and they happened from a fissure that erupted all of this material, basically. You may recall the in the last chapter, when we looked at large igneous provinces, I showed you where the Columbia River basalts laid. And there's also an image on your book, I think it's image 5.32, that shows you the different basaltic provinces that have occurred due to this mantle plume rising, along with different hotspots. So check it out. The picture on the top right is of the Gorge Amphitheater, which is near I-90 going from Spokane to Seattle, near the Columbia River, as can be seen from the picture. It's a really cool place for concerts, and I'm sure some of you have been to one or two or more of them there. Okay, so fluid basaltic magmas tend to generate two types of lava flows, which are known by their Hawaiian names. The first one on the bottom right of the slide is A'a flows. These have a rough surface or jagged blocks with sharp edges and spiny extrusions. They look kind of crumbly, and they tend to form when the lava is a bit cooler. The second type of lava flow is called pahoehoe. These have smooth surfaces when compared to A'a flows, and it looks quite ropey, if you would. Usually you are able to tell the flow direction from looking at the rope features that you're seeing here in the slide, for example. The flow of the lava is perpendicular to the elongated side of the rope-like feature. So in this case, you're seeing the elongated side of these ropes kind of going from left to right. So the flow of this magma is sort of, I guess, up towards the down part of the picture. Pahoehoe occurs when the lavas are hotter usually. So, lava flows may first start as pahoehoes and then turn into aa flows, but never the opposite, because lava doesn't go from being cooler to being hotter. It usually always cools down when reaching the surface and becoming flows.